Okay, so in this video, what we're going to do is we're going to take a look at the diode, or diodes in general, and we're going to introduce the concept of what a diode actually is. Now, as you would have learned in an introductory semiconductor physics course, a diode is nothing more than a p-n junction, or a special sort of case of a p-n junction. But this is a sort of general thing that we have here. Two-terminal device, p-type material, n-type material, and they're fused together by some means. But what we're more interested in is what the electronics sort of rendition of that is, which is a diode, which looks really like a play button, as you would see on a DVD player or a VHS player if you're a little older. And so this here is your diode. It's basically a triangle with a little bar here, and the bar obviously has some significance, which we'll go into a little bit later. But basically what you have is you have on this side you have the anode, and this side you have the cathode. And then we can define this voltage here, or we can assume that the diode will have a voltage in general. We call it VD for V diode or diode voltage. And then we can say that there is a current that would obviously flow through this device, and we can call that current ID, simply for diode current. So what do we want to look at here? What's important? One thing to note here is that VD is the diode voltage. So let's make note of that. So this is the diode voltage, and we basically define VD is approximately equal to, it's not exactly equal to, but it's equal to the anode voltage minus the cathode voltage. The reason I say approximately and not exactly equal to is because there are some approximations that we make when we deal with the circuit symbols. So actually the diode voltage would be something a little bit different, but for all intents and purposes of electronics, this is the definition that we would use here, the anode voltage minus the cathode voltage there. And we say that ID is the diode current, as mentioned previously. So this is the diode current. And we say that this flows from A to K. So the direction of the diode current must always be from A to K. Or if you think about this as being some sort of a funnel, let's say, so if you imagine that this is some sort of a funnel that looks something like this, you can imagine that all of the electrons, if I'm pouring in electrons, let's say like this, people like to use the analogy of water. I personally don't, but it's a good way to think about it, I guess. This is your current, so this is your diode here, so your current can only go this way, and you can't really, well, you technically probably could push some that way, but imagine that you can't. So basically this thing's like a funnel, is where we are, I guess, at this point. So now, what do we want to talk about next? What do we want to talk about next? We want to talk about the different types of models. Let's talk about the different types of models. So we have models here. Now there's three different types of models. There is the ideal, which we will talk about in this video. There is the constant voltage. So this is constant voltage, and we'll look at this one in a future video. And this one here will be the exponential model. So these are just different ways of modeling the exact same thing. Obviously, some will have more benefits, or well, different benefits, I guess you could say, not more or less. It's a matter of what you're looking for and what type of problem you're looking to solve. But in this case, what we're going to do is we're going to talk about the ideal diode. So as mentioned, the other two, the constant voltage and the exponential model, will be looked at in a future video. But for now, what we're going to do is we're going to look at the ideal diode. And as you may, well, you may not, you may, speculate to begin with that the ideal diode does not exist. So there is no such thing as an ideal diode, practically speaking. In terms of analysis and for the sake of the work that we're doing here, it's actually a very good approximation, and it's a very good way to get used to solving these types of problems, because diodes are nonlinear devices, and we'll explain what we mean by nonlinear devices in a second here. So what I want to do is I want to draw what we call a IV characteristic, And the reason we call it an IV characteristic, and for some reason it just got off the grid, but that's okay. The reason we call this an IV characteristic, so if I call this I and I call this V, basically what it does is it plots the current versus the voltage of the device. And so for an ideal diode, what we have is, we have that the diode voltage, well, the diode current for negative voltage is 0, and then all of a sudden what happens when I equals 0 at this point, let's imagine this is 0, and if that's 0, what happens is this current is going to spike like this. Now we know obviously that this can't happen, because this, if I were to extend this graph, would go to infinity. We know that you cannot have such an infinite current, but basically what that means is it becomes a short circuit, and then the current obviously through the diode would be limited by the circuit around the diode. And so then we have how to represent it. So then how do we represent it? So let's talk about representation of these two characteristics. So what I'm going to do is I'm going to call, well, I'm not going to, what we do is we call this region the reverse bias. So this is reverse bias, and this is forward bias. And so for this region you have that I equals 0 and VD is less than 0. For this one you have that V equals 0 and I is greater than 0. And how much greater than 0? Again, that's limited by the circuit around it, because, you know, although the device's current can spike up, the actual current through the device cannot spike up. It must be limited by some external resistors and whatever type of, you know, circuit that it's actually in. So what we're going to do here is in the representation of this ideal diode, we can break up into two regions. So we have the reverse bias representation of it, and then we have the forward bias representation of it. So under two cases, we'll have two different sort of ways of modeling this diode. And so what happens is, when it's reverse biased, what you will see is that this diode will become an open circuit, because if you think about this characteristic here, I'm saying that when VD is less than 0, I is equal to 0. The only way I can ensure that I is equal to 0 is if I create an open circuit here. So what I'm going to do is I'm going to call this voltage here VD, and I'm going to call this current here ID, and clearly ID is equal to 0, and V in this case, VD is less than 0. So what we have here is we have that ID is equal to 0 and that VD is less than 0. So these are our two conditions that must be satisfied in order for this thing to be reverse biased. And then in the case of the forward bias, if I want this current to be, well, spike up and then V to be 0, if V is 0, as you would know from basic circuit theory, if VD is going to equal 0, sorry, I forgot to draw the ID here. So we have ID here. If VD is going to be 0, then it must be a short circuit. So in this case, ID is greater than 0 and VD is equal to 0. So these are sort of like, this is what we would use. So to recap, yes, this is the diode model. Like, this is what the diode looks like in a circuit, but I can't solve anything with this if I use this like this play button funnel looking thing. I can't solve anything using this. So what I have to do is I have to understand that under different circumstances, the diode behaves as a different type of device. And so these are the sort of models that you'll be using to solve the actual circuits, and we'll see that in an example shortly. But one thing I want to mention is that I referred to this as being a non-linear device, and so I just want to spend a minute talking about that. If you think about a resistor, let's say, a resistor would have an IV characteristic that looks something like this, right? Where the current and voltage are related by the resistor, or the value of the resistor, right? Because we have in a resistor, you have that V equals I times R, right? And now no matter what, if the voltage is negative or positive, this is always true. What you'll notice about our diode is that under different regions or under different conditions, it behaves differently. So we call these devices non-linear. And for that reason, because they don't always behave the same way. The resistor, you can sweep the voltage from positive to negative. It'll always behave the exact same way. The diode will turn off at some point. It'll turn on at some point. And I'll probably add that here as well. Under reverse bias, we say that this is off because it's not conducting. And then under the forward bias, we say that it's on. So an on diode is referring to a forward bias diode, and a reverse bias diode, or an off, is referring to an off, and vice versa. So that's what we have for the actual setup of how to deal with these problems. So now you might be wondering, how do we solve problems with these? Because how do we know if it's on or off? So let's talk about steps to solve diode circuits. Now these steps are really applicable in the case of the constant voltage as well as the ideal. What happens is the actual model that you replace them with when they're on or off changes. And again, we'll see the constant voltage in a future video. But for now, what we'll do is we'll look at an example after we lay out these steps using the ideal model. So the first step is to assume a state. So you either assume it's on or it's off. And yes, as you may have just realized all of a sudden, the more diodes you have in your circuit, the more possible states you can have, because every diode can have two possible states. So for the number of diodes, you have 2 powered by n states, assuming n is the number of diodes. So for 2 diodes, you would have 4 possible states, but only one of those states is actually correct, is the thing we should understand. Yes, you would have 4 possible states, but of those 4 possible states, only one of them can ever be correct. You can't have multiple states be correct for a single circuit. It doesn't make sense that way. And we'll see this in an example after. So we assume a state. We replace the diode with the appropriate model. So if we assumed on, then we would say that it's the short circuit. If we would assume off, we would assume it's the open circuit, and so on. And then in the case of the constant voltage, which we'll see later, it would be obviously a different type of representation, but you would replace it with that. You would solve the circuit, and now by solve the circuit, I mean you find the voltages and currents that you're looking for. And then we have, this is the crucial step of the entire process. So what we do is we check if diode conditions are valid. Now what does that mean? So if I assumed on, then I have to check if the current's greater than 0. If I assumed off, then I have to check if the voltage is less than 0, because these are the 2 conditions, right? So by saying that the diode is on, I've assumed that it's a short circuit. If I've assumed it's a short circuit, then I know that the current must flow from, in this case, let's say the anode to the cathode like this, anode to cathode here. I've assumed that this is on, therefore I know that the diode current must flow this way. If it doesn't flow this way, then I know I did something wrong. On the same token, if I go to the reverse bias case and I assume that this diode's off, that means VD has to be less than 0, because as seen in our IV characteristic here, whenever the diode is off, I'm assuming VD is less than 0. So if I assume that this is an open circuit, or that it's off, as a result it's an open circuit, and then I determine VD and I find that VD is greater than 0, that means I've done something wrong, and that means the assumption was not valid. So that's what I mean, check if diode conditions are valid. And then the last step is repeat process with different assumption if invalid. So if it's invalid, then you would have to go back, assume the other state or a different combination of states, replace the diode with the appropriate model, solve the circuit, all the voltages and currents, check if the conditions are valid, and then you can go. And if it's correct, then you can go from there. So these are the steps. We call this thing, I mean, if you want to get fancy and give it a name, you call it the method of assumed states, because you're assuming states and it's a method. So as the name would suggest, you would assume a state, solve some stuff, and then that's where you're at. So now what we're going to do is we're going to take a look at an example, and it's a relatively simple example, and it's created for the purpose of illustrating this entire method here. So we're just required to solve the circuit. And again, like I said, the circuit itself is quite simple in nature. It's a single diode, so you have one resistor here, and you have your diode here, connected between there and ground, and you have a second resistor there, and then you have a second voltage source here. So you have plus, sorry, that's not 16, that should say 6 volts. This is minus 6 volts. We can call this diode D1. We can give this the values that they need. And so those are 1K and 2K. And we have some currents here that we're interested in. So I have, this is what we need to solve really, is I1, and then I2, and then ID. Well, ID we're going to solve for as we go along, but you know, it's good to have that there as well. So what do we do here? We say that the possible states are what? This diode can either be on or it can be off, right? And like I said, if you had multiple, then you could have had one diode on, the other one off, both on, the other, like the opposite case, on, off, and then both off. So it depends on how many diodes you have, that the possible states you have. In this case, you have on and off. What I'm going to do is I'm going to start with off, simply because replacing something with an open circuit makes the circuit a little bit simpler in my opinion. So I'm going to assume that it's off. So what I'm going to do is I'm going to assume diode is off. Now if the diode is off, then I'm left with, well, and I would always recommend that you redraw these circuits because they tend to simplify themselves quite a bit when you redraw things. And that usually makes the analysis a little bit easier than if you're just looking at it trying to imagine. So this is minus 6 volts, and this is 1K, and this is 2K, and clearly in this case, what did we have? We had I1 here, we have I2 here, and in this case, clearly I1 equals I2, right? One thing we should also note is that this voltage here is equal to VD, meaning that the voltage at this node here is the one that I'm interested in. If I can solve for this voltage, it's the same voltage as VD, and what I need to do is I need to prove that this is indeed greater than 0. So what I'm going to do is I'm not even going to solve for I1 and I2 first. I'm going to solve directly for VD using a voltage division. And if you haven't already, there's a voltage division video in which I show how to do voltage divisions with two sources like this. Because with a single source, it's relatively simple. But you'll notice with two sources, there's going to be a contribution from each source as seen at that node there. So what I'm going to do is I'm going to solve for VD, and what I'm going to say is that VD is equal to the positive 6. So the contribution of the positive 6 seen there is going to be 2 over 3, because you have 2, well, maybe we can do it in 2 steps like this. So it's going to be 2 over 1 plus 2, and then I'm going to add that to the negative 6 contribution, and the negative 6 is going to be on the opposite side. So it's going to be 1 over 1 plus 2, or 2 plus 1, whichever one you want. And if you solve this, you'll find that this is equal to 2 volts. And so this 2 volts here that we have, what we need to do now is we need to go up and we need to check what's going on. We assumed that the diode was off. We assume this is an open circuit. Now, when I go back here, I see that whenever my diode's off, my voltage has to be less than 0. But I found that my voltage is greater than 0. This is equal to 2. 2 is clearly greater than 0. That means this assumption is incorrect. So, what I'm going to do is make a note here and say, since VD is greater than 0, Assumption incorrect. Now I can go to the other state, because I know that if it's not this one, it has to be the other one. And I know that the other one has to be correct unless I make a mistake somewhere in the calculation, which is a completely different story. And now if I assume that it's on, then I can replace that diode with a short circuit, like so. And then I can resolve the entire circuit, which is still a relatively simple circuit. This is positive 6 volts. This is minus 6 volts. This voltage now is 0 volts since it's shorted to ground, which is convenient. This is 1K. This is 2K. And again, I have this I1, and I have this I2, and I have this ID. So this becomes relatively simple because I know this voltage, I know this voltage, and I can just take the difference and divide it by the resistor to find I1. So I get that I1 is equal to 6 minus 0 divided by 1, which is 6 milliamps. And I can do the exact same thing for I2. I can get I2 is equal to 0 minus 6 divided by 2, which is equal to 3 milliamps. Now I can either use my logic or I can use KCL, and I can say that I1 is equal to I2 plus ID. If I rearrange and solve this, then I get that ID is going to be equal to 3 milliamps. Now, this ID that I have here is greater than 0, right? So ID greater than 0. And if I go back up here to this, to these initial, sort of groundwork that we laid here, you'll notice that for the forward biased diode, or the on diode, ID should be greater than 0, according to this characteristic here. So VD is equal to 0, which is the short circuit, which is what I forced the circuit to do, and then I check that ID is greater than 0. It is indeed greater than 0, and therefore the assumption is valid. So we're good. And so just to recap what we did here, we laid down the sort of foundation for the diode, and we talked about the ideal diode in this case. And the ideal diode is when it's on, it becomes a short circuit, and when it's off, it becomes an open circuit, governed by this IV characteristic here. We laid out some steps as to how we can actually solve these circuits, and we said that the method was to assume a state, replace it with whatever model we assumed, and then to solve the circuit to find the voltages and currents, which is what we did here. And then we had to check if the diode conditions are valid, which is this last, well, in this case it was the only step. In this case it was the sort of last step. And if that doesn't work, or if it's found to be invalid, then you repeat the entire process with the other side. So you'll notice we went off first, and we found that it was invalid. Then we repeated the process using on. If we had went on first and found it was valid, we would have been done there. Now, is there any way to know which one it is beforehand? It's kind of difficult to tell in more complicated circuits. If you have a simple circuit, you can usually figure it out based on, just ballparking, I guess you can say, what the number should be of the voltage and what the voltage drop should be. But in more complicated circuits, it's very difficult to actually predict how the diode will behave. So it's usually better to take a look, and it comes with experience. To be honest, there's no way to do it. You would just imagine that maybe I've solved a circuit like this somewhere else previously, and in that circuit I found this to be the result, so this might be true. But again, you always have to check these conditions, because if you don't, there's no way of knowing for sure what the actual state is. So if you have any questions, leave them down in the comments below, and I'd be happy to answer them. And other than that, I want to thank you guys for watching. I hope you found this video to be helpful, and if you haven't already, like, subscribe, and support the channel, and we can have notifications for you whenever a new video is uploaded, so that you can get it as soon as possible. And we'll see you in the next one.